Okay, yeah, thank you for the introduction. Yeah, I'm a PhD candidate. I'm also the infrastructure guy in our institute, and I'm currently founded in the sustainable software call from DFG, and the software I'm co-writing and using, I'm also employing the actual research I'm supposed to be doing, especially in the localized reduced basis method branch. I'm guessing very few, if anybody, has heard of this. Yeah, so I'm going to tell you a little bit about the software library, PyMore, which I'm working on. I'm going to tell you about my personal or project's problems with unit testing, and how we're now trying to use a different, better approach, let's hope. And yeah, the last bit will be calling on everybody to help me. Okay, so what is PyMore? It's a Python library. It's not an application you can just run. And it's you can use it to build your own model order reduction applications. If you don't know what model order reduction is, the model involved is, for us, something mathematical, usually involving a parameterized PDE or an LTI system. And well, the mathematical description is something like this. You have a function that maps from some big unknown parameter space to a solution, and maybe from this solution you want to compute some single number. This is the quantity of interest, but this doesn't really matter. I'm just trying to show you that there are possible infinite dimensional spaces at play here where we get parameters from. So, and usually model order reduction is used in one of two settings. Either you want to calculate a lot of quantities of interest for any number of parameters. This is the many situation, many queries. Or you have to be in some kind of real-time setting where you no matter what parameter you get, you have a deadline of, I don't know, 15 microseconds to get a solution. And I'm not going to tell you what the actual model order reduction techniques are because, well, that's a couple of lectures. This is a graph for the many query situation, right? You have a somewhat linear explosion of runtime. The more solves you have to do for different parameters, the more time you spend. And this red curve is the visualization of a model order reduction technique. You have to invest time up front. This is the very steep slope at the beginning. And then at some point you have a crossover point where you're cheaper because every single solve after the initial expenditure of effort gets much faster. And depending on the sizes of spaces and whatever, this graph can look this way, can look magnitudes of orders better or worse. This is very problem dependent. Okay, if you want to know more about the actual PyMore, you can read our paper. You can come to the first ever PyMore school in October in Magdeburg. But you'll have to know model order reduction beforehand. We're only teaching about PyMore, not the underlying techniques. Okay, so we've started PyMore 7-ish years ago now in Münster with 3 people. We're now somewhere between 12 and 16 contributors, 4 of them fairly regularly. We have a largish code base, lots of commits, open source. We're hosted on GitHub. And of course, no, I say of course, but we do have continuous integration tests. Right from the beginning, I think, we had a setup on Travis CI where every commit pushed, gets built and tested in some way. Recently, I migrated away from Travis CI to use infrastructure we have at our institute and in the university at large. The method is pretty simple, I say. We just have a Docker image with lots and lots and lots of dependencies, libraries, external PD solvers and whatnot. And our pipeline gets executed in this. We use PyTest to run the tests. We do some deployment for Python wheels and check if everything installs on different platforms. And we do some very limited testing on OS X and Windows, but that's actually just running a demo. Okay, so this is what our integration pipeline looks like at the moment. We can run a bunch of stuff in parallel. On the test column, there are different configurations in which the tests are run, and we have a very varying runtime of each. But a single build step can take up to 55 minutes. And this is on hardware in our institute, which is recent and fairly large sized. So, and these are a mixture of traditional unit tests where we input a given data into our function, check the assertion, the oracle, as I just learned, and see what the output is. And we have some system tests where we run a full model and we have an analytic function that is the real solution and we can check against that. All right, so what are the problems I mentioned that we and I have with unit testing? First of all, we found that people aren't actually very good at selecting what to test. So the developer can have a very strong bias to select test cases he knows are okay and the software will work with them. This is a problem. Test parameterization can be difficult to formulate. You have to run the same test for a bunch of different scenarios, right? For us, this is different backends for PD solves, different meshes, different whatever. Different implementations of our vector abstractions, and so forth. You have to write this, and especially in PyTest, this can be looking very not so nice. If you then want to compose this functionality into something that is a more expressive system, so where you have to execute a bunch of tests in some order to check if your model pipeline still works. This is, again, something you have to write manually. It's effort. And the last bit is, I don't actually know if my tests are good. I have no real metric for it. Then the question is, how much unit testing should I actually do? Do I aim for 100% coverage? Is 70% okay? Does this actually mean anything? And how much of the input space can I cover? Should I cover? This is a very big problem, especially for us, where we have unknown dimensional parameter spaces. Our vectors can be 10,000 dimensional, time series, and whatever. The next question then is, if I can do it, should I do it? Is this okay if my test runs for 2 days? Does this help me? And of course, can I run it? Is my local computer environment able to run 13 of these tests concurrently. And there's practical problems, especially for our setup for us. In PyTests, the parameterization runs through something called fixtures. And for us, it's always a problem if a single failure happens somewhere in the code, and the fixture is very complex. It's composed of multiple parts. And the fixture itself has a large input space. So what happens if I want to reproduce a failure? I currently have two options. I can hack the fixture manually, change whatever I need to just produce one result, do a complex breakpoint. This is very hard for something that has very large data. We've looked, and to improve the situation, we come across something called Hypothesis. This is a Python library that implements property-based testing. The idea is very old in computer terms. The original quick check, which this is a re-implementation of, was developed, I think, in the late 80s. This is a library that plugs into a couple of different test frameworks, which for us in this one case that I was able to spend time on now, makes for much simpler parameterization. It is much easier to compose tests with it. It has the very, very nice feature of outputting a decorator. If a test fails, you put it on your test function. It reruns the exact test it did before and only this. You can add your edge cases manually. And, well, you can configure how much, I think I skipped it. Oh, okay. You can configure how much data Hypothesis produces to input into your tests. So your everyday tests can get 300 points of data, and once a week you run 3,000. And my favorite one, PyCharm actually can resolve these kinds of fixture decorators, and if I run PyTest with its fixtures, I get nothing. It doesn't understand PyTest fixtures. Okay, so this is a non-working subset example of our fixtures for a array abstraction. This is relatively complex because we need different setups. We need situations where we get two arrays of same size with values. We need setups where we get ones that you can't actually add, so we get an error and so forth. And this is, I think, just one where we get actually one vector with prescribed elements and a list of indices. This is, I mean, I can read it. I wrote parts of it. I don't understand this. Okay, so the test empty function then gets the vector array fixture that's defined 2 lines above, and this is the PyTest fixture magic that nobody understands. Okay, now with Hypothesis, you define strategies to generate input data for your tests. The top line is a strategy for integers. This is currently actually implemented in a branch for our project. And well, these strategies search their input space. I'm not going to say randomly, but it's a way implemented that you get edge cases. If you don't disallow it, you get infinities and so forth. And now what's here on the slide actually produces about 6 or 7 different configuration options with times of vectors, length, different number types, and it's still pretty dense. But you get one function that defines all your data output. If you look at the whole setup now, it's much more readable. You don't have any magic numbers in it. It's easily extensible. You can do the same setup for different backends. And composing different strategies into a new strategy is trivial. It's the fourth line from the bottom. It's an operator. Right. This is how you compose strategies. And hypothesis does the rest for you. So this is a major improvement for us, because before we had to chain parameters next to another, and this is much nicer. Yeah, as I said, this is only the first bit of code refactoring that I've started. It's very little effort. As of now, I've basically only changed how our unit tests get data. It was fixed lists before. Now there are strategies that generate whatever data I've told it to. And it's only, and I've not implemented this fast test for development. Weekends can run longer tests. This is all not done yet. The actual bigger part, I think, what hypothesis enables you to do is define a state machine as a class. You define transformations between your state as rules, it's what it's called. You can then implement a check that some property of your state still holds. And the library will combine transfer functions in every which way, generate inputs, and strategies like you defined, and will try to fail your test. And if it finds a failure, it will try to shrink the sequence of input it generated to the minimal one where the test still fails. I've only come up with a very simple example as of now. This is a state machine for basis testing, so a vector space basis. You define a member that is a bundle. So basically the library will then generate new bases from all functions that have a target for this. I've cut out the actual basis generation because it's a little more involved. And then you can define transfer functions on your state where you know a property will still be, should still hold after the transformation. So if I run a basis through a Gram-Schmidt algorithm, I know it's still a basis afterwards. And if I want to display any given vector of the same dimension for a basis, I know that I must be able to solve this linear system here. So now if I run this, hypothesis will generate a list of inputs for basis generation. We'll pick up bases from this bundle, put it in Gram-Schmidt, put it in coefficients, outputs, get in new bases, and so forth and so forth. And I don't have to tell my test casing how it should compose new tests from the state machine. This, of course, is a pretty trivial example, but it still works. Okay, so to recap what I found if I want to use hypothesis. It's much easier for me to let my tests run on a very large input space. I don't have to manually write how many data points I get. It searches edge points, it's edge cases for your input data. So as an example, we've never input infinities in our arrays before. We didn't mix complex valued arrays and integer arrays and something like that. And I think our values were kept at -1 and 1, and some algorithms actually behave very differently if there's magnitude of order of difference in your input data. And this is everything that just pops up now, and we have to fix a lot and stuff. For me, it's a huge boost in usability if I actually find an error. It is, however, for me and us, somewhat hard to actually apply this on our code. Because you need these properties or transformations, and you still need something to control against. And so for the basis, it's pretty easy. If I put in a vector, I know I must be able to solve the coefficient matrix. But for other algorithms and operators and discretizations, this is quite unclear how this will work or if it will work. But for this very data-driven vector abstraction, this was, I think it's great. Okay, so, and something that I've in looking into this, I found I was very lacking is practical examples and guidelines on how to actually write unit tests. I found literature in software engineering research that I don't understand as a mathematician. So I don't speak the language. I found 100% coverage is great, you're done. This is very untrue for us. And well, so basically, I would have hoped to have a repository of some kind with guides. What do other people do? What failed for other people and stuff. So if anybody wants to join or doesn't know of this, if it exists already, please contact me. Yeah, that's it.
Thank you very much, Renè. Okay, are there questions? Otherwise, was there one? No, okay. I have one. Maybe it's a very practical one. Maybe I didn't perfectly get it. Like when you do this testing and it generates the input data for you, do you test mainly the functionality of your code, whether it breaks, or do you test the quality of the outcome or the reproducibility or the, you know what I mean?
Yeah. For this part where I've started using a hypothesis, this is real unit testing for our vector abstraction. So like, does the scalar product of two orthogonal vectors still produce 0?
Ah, yeah.
Something like this. We haven't used this in a
integration testing
no,
more complex?
This doesn't run a parameterized model or something and where we then check if the truthiness of that model is still there. And this is actually one of the problems if I want to use this. I'm not super sure how this will work.
It would be great to join forces here. I think some problems are similar. Yeah. You two first and then you, okay?
Yeah, maybe a small comment. I'm a chemical engineer by training, and this sort of reminds me of what is sometimes done in system identification. So you have very large, super complex input and output spaces.
Yeah.
And they might know the input spaces up front, but they have no idea what the output space looks like, and they're definitely not boxes of any sort. And what they do from time to time to properly identify a system which they have as a form of code or as a form of experiment, they try to maximize the distance between points in those inputs and output what they've already sampled.
Okay. Yes, so a greedy search in the error measure of some kind. Okay. Yeah, thank you.
If you let the test run twice, would it sample the same input data or different input data
if you don't change the, right. The question was if I run a test twice, does the library input the same data? Yes. If you don't change the configuration, as far as I understand, the strategy is deterministic.
My question is quite on the same campaign. So let us say a test fails for certain inputs, and then I fix it, and then at some point during the pipeline, during the development history, somebody breaks it again. What are the chances that hypothesis will forget about this edge case?
Okay, so the question is if a check fails, I fix it, and how are the chances that the same input data is reproduced at a later date, right? Well, the strategies can change, of course, with library versions and whatnot. But you can actually use a functionality of the library to put exactly that input data that you checked as an example. There's extensive databasing behind the scenes where you can, and I'm not sure if one should do that, but you can basically ship the entire library of everything that has been done yet already. And that would ensure that the test is rerun if it failed at some point. Or, of course, the explicit decorator to mark the function.
I'm a bit afraid we have... Oh no, there's one more question is possible, if somebody wants to. Okay, I have a question, just very practical. You said you switched to Docker, so that's the frame you have around that everything gets reproducible, or why did you do that?
Well, I wouldn't say it gets reproducible. There's a lot of challenges in actually getting reproducible Docker builds. No, this was purely practical, because we have a lot of dependencies that are C++ libraries that use very large stacks of support libraries. And if you try to install this on a machine, that's fine. If you try to install this on 20 machines, that's nonsense. This is basically something for us to get a, well, reproducible environment to execute in, but it's still not really reproducible because some stuff gets installed at runtime, which we want, because Python dependencies update all the time, and if a user gets a new library and our code breaks, we want to know that. But yeah, this is mostly practical for us.
Just to distribute it amongst...
Yeah. Well, you can use our images for local development just as well. So I don't install all the PD solvers in my machine. I just run my Python interpreter in the Docker image.
Okay. Thank you very much.